The next person that we have coming up is Nicholas Buffy from Harvard University. And his field is in soft condensed matter physics, and his advisor is Chris Rycroft. And he did his practicum at Lawrence Berkeley National Laboratory in 2017.
And I'm going to talk about some of the work I've been doing modeling plastic deformation in amorphous materials at the continuum scale in parallel in the quasi-static limit. So the materials of interest are sort of test case for our algorithms are going to be bulk metallic glasses. So a bulk metallic glass is a solid material held together by metallic bonds with an amorphous atomic scale structure. On the right-hand side here, I've contrasted a typical crystalline structure for metals, where the atoms are arranged in a regular lattice, with an amorphous structure where we just have short range order and no long range order. So in a metallic glass, these bonds are metallic, unlike traditional oxide glasses, which you see in glasses that you drink out of or windows. And the fact that they're metallic is very important. It leads to a dense packing, which can make these materials stronger than steel, yet at the same time, they maintain a high strength to elasticity ratio. You can see this in the plot here, where the x-axis is strength to elasticity ratio, and the y-axis is the yield strength. You can see that metallic glasses are very high up and very high to the right. And at the same time, they can be processed and molded like a plastic. So you can basically form them into any kind of shape, like think about cell phone cases or biomedical implants, any kind of situation where you need some very strong material in a very specific shape. But at the moment, we can't actually use metallic glasses for any of these applications because they sort of fail along a catastrophic failure mode known as a shear band. So a shear band is a rapid and narrow localization of plastic deformation due to a strain softening instability. By strain softening instability, I just mean that when plastic deformation begins to occur in a given location in the material, it becomes much more likely to continue to occur there. So you get this sort of runaway phenomenon. Here are some experimental images of shear banding in metallic glasses under compression testing, where you can see all these thin little bands propagating across the material, and these lines are basically just where the material is about to fail. So shear bands are pretty interesting from two perspectives. One is fundamental physics. At the moment, we actually do not have a generally accepted theory of amorphous plasticity, the microscopic origins of amorphous plasticity. And any such theory must be able to predict the structure and formation of shear bands to very high accuracy. So they're a really good test bed for any theory if you think you understand what's going on with amorphous plasticity. On the other hand, bulk metallic glasses are a very important class of materials with very interesting applications, but as I said on the previous slide, we can't use them until we understand and control shear bands. So I just said there's no generally accepted theory of amorphous plasticity, but there are some that have been very successful. We'll focus on one in this talk called the shear transformation zone, or STZ theory of amorphous plasticity. So the STZ theory posits the existence of small localized regions called STZs that are randomly distributed throughout the material that are likely to undergo small-scale plastic rearrangements when the material is subjected to external shear. So here's an image of an amorphous material where I've highlighted two STZs. They don't look any different from the rest of the material. You can't really distinguish them by eye. But when the material is subjected to shear, you'll have one cluster that will transition to a cluster basically in a different arrangement. And every time one of these rearrangements occurs, the material accrues a small increment of plastic strain, and it's sort of the conglomeration of many such events that leads to macroscopic plastic deformation. So these STZs, it comes out of a statistical mechanical treatment, are randomly distributed in a Boltzmann density throughout the material in an effective disorder temperature denoted by chi. And chi, for any physicists in the room, is much like a usual temperature. It's measured in Kelvin. It can be obtained as the derivative of a configurational entropy with respect to a configurational energy. But in general, it's far from equilibrium with the usual thermodynamic temperature. OK, so with this in hand, we can design basically a continuum scale theory for plastic deformation in metallic glasses. What we'll describe our material are the 6 components of stress, the 3 components of velocity, and the effective temperature. So we need basically a partial differential equation for every one of these variables that we can solve. So bulk metallic glasses are very stiff, so linear elasticity is a good approximation, which just says that some suitable time derivative of the stress tensor is given by the contraction of the stiffness tensor into the elastic part of the rate of deformation tensor. The rate of deformation tensor, the total rate of deformation tensor, is the symmetric part of the velocity gradient, and we make an assumption called the hypo-elastoplastic assumption, which says we can additively decompose the total rate of deformation tensor into a sum of elastic and plastic parts. This lets us rewrite DEL as d minus dPL. We can compute d from the velocities, and dPL will be given to us by the STZ theory. The velocity field evolves just according to Newton's law, force equals mass times acceleration. And then we need some stuff from the STZ theory. You basically need an expression for dPL. So tensor dPL is given to us by scalar dPL times the function of the stress tensor related to the deviatoric stress. The evolution equation for the effective temperature is essentially a heat equation for the configurational subsystem. The first term is related basically to the work done on the configurational system, and it sets the rate of relaxation to this asymptotic value chi infinity, which is generally quite high. And then there's a diffusive term. This constant L sets the length scale of shear banding, and it's plasticity mediated. So if there's plastic deformation happening in a given location, the effective temperature tends to diffuse faster. So finally, scalar DPL has a ton of material parameters, so I'll just lay it out qualitatively. It's basically given by the density of STZs times an Arrhenius barrier crossing term for one of these rearrangements to occur, times the rates for forward and reverse transitions of one of these rearrangements, times a term which asymptotically approaches 1 as S bar, a measure of local stress, approaches infinity, times 1 if the local stress is above the yield stress, which is the quantity that says basically when plastic deformation begins to occur. OK, so with all these equations in hand, we can just discretize them using finite difference stencils and solve them. But there's a problem here that elastic waves move very fast in these materials. And in particular, they move very fast in comparison to the time scale of interest on which plastic deformation occurs. So if you try to just use your favorite discretization technique, you will resolve elastic waves, and your time step will be limited by the CFL condition. So you won't be able to simulate large systems or long times that we actually care about. So one thing you can try to do is scale to the long time limit. And if you do that, you'll find that you retain the evolution equation for the stress tensor, but the evolution equation for the velocity field will be replaced by a quasi-static constraint on the stress tensor that it must remain divergence-free. So now we have a situation where we need to solve for the stress tensor, which depends on the velocity field through d, but we can't actually solve for the velocity field because the evolution equation for the velocity field has been replaced by a constraint on the stress. This sounds like a difficult problem, but actually it was solved in incompressible fluid dynamics, where if you take the incompressible limit of the Navier-Stokes equations, you find that you retain the Navier-Stokes equations, which depend on the pressure, but the evolution equation for the pressure field has been replaced by an incompressibility constraint in the velocity field. So this was solved by Alexander Chorin a long time ago, where he basically developed a method called a projection method, where you take an intermediate step denoted by V star. This V star does not obey the incompressibility constraint. And then you project it back onto the manifold of incompressible solutions in such a way that you can solve for the pressure field in the process. Clearly, there's a strong analogy here between the stress tensor in our formalism and the velocity field in Navier-Stokes, and the velocity field in our formalism and the pressure field in Navier-Stokes. So we're going to develop an analogous algorithm where we take an intermediate step to find sigma star. It will not obey the quasi-static constraint. And then we'll project it back onto the manifold of quasi-static solutions in such a way that we can solve for the velocity field. So 2 remarks about this. Any algorithm, any projection-based algorithm for Navier-Stokes can be mapped over to hypo-elastoplasticity in this way. And this analogy is independent of the plasticity model. We're using the STZ theory to model bulk metallic glasses, but you just need an expression for DPL, and then you can use this algorithm. OK, so how do we actually develop an algorithm like this? Well, we take the hypo-elastoplastic equation, and we just discretize it in a semi-implicit way. We evaluate all the time derivative terms at the nth time step, the C contracting to DPL term at the nth time step, and C contracting to D at the n+1th time step. We first compute sigma star by doing what we call the advection step, where we just drop the C contracting to D term. And we do this in a parallel way. It's parallelized using domain decomposition in MPI, along with the chi update. And it's solved on a staggered grid with sigma and chi at cell centers and the velocity field at cell corners. Now, if we knew the velocity field at the n+1 time step, of course, we could compute sigma n+1 just by adding in the C contracted into D term. But we don't know the velocity field at the n time step. So what do we do here? Well, we know that the divergence of sigma n+1 must be equal to 0. So if we take the divergence of this equation and rearrange, we'll find this expression here. And this is actually a linear system for the velocity field, because D just contains linear derivatives of the velocity field. C contracting to D is a linear operation, and divergence of that is a linear operation. So we can solve this using standard techniques of numerical linear algebra. The source term divergence of sigma star is known at this point, because we've already computed it. And we do this using the multigrid method. We wrote our own custom C++ implementation. It's also implemented in parallel, parallelized using MPI, and interfaced with our advection step. Because we do this in MPI, and if you're familiar with multigrid, the discretization changes at every level. We compute the optimal processor decomposition at every level, and all the processors at every level know which processors they need to communicate with on the levels above and below. And we also implemented this with C++ templates, so we can solve for an arbitrary data type at each point in space. In our case, we need a 3-vector, but you can do whatever you want, complex numbers, 2 vectors, 4 vectors, and we'll actually release this software for public use in the future. OK, so with all that, now we can solve for plastic deformation at long times for realistic system sizes, but there's a problem that we don't know how to initialize the effective temperature field. On the other hand, there's another simulation method, electrodynamics, which is great because it's physically exact, unlike our continuum scale model where we needed these equations and we needed the STZ theory, we needed to know something about our material. Molecular dynamics also contains complete information about the atomic structure, while this has been sort of coarse-grained into internal model variables like the effective temperature and the STZ theory. But MD is computationally expensive, whereas continuum scale simulation is much faster and it's much more scalable to large computers, essentially. So a great situation would be one in which we could take an MD configuration, compute the effective temperature distribution from it, pipe that as an initial condition into the continuum scale model, and scale that up and throw it on Titan or Summit or something like that and have a really accurate, really large simulation. But to do this, you would probably want to do some sort of statistical matching procedure between MD configurations and continuum scale simulations to approximately match shear banding dynamics. But we can't really do this right now due to a difference in the boundary conditions. MD uses Lees-Edwards boundary conditions, where the system of interest denoted in yellow is periodic in every direction, but the periodic copies above and below move with the prescribed velocity, whereas we use parallel plate boundary conditions at the continuum scale. So this difference, because shear bands are an instability, is really enough to destroy any attempt to match configurations. So we've developed a method to implement Lees-Edwards conditions at the continuum scale. We define a reference domain, capital X, and a physical deformed domain, lowercase x. And we assume that you can map from the reference domain to the physical domain using a time-dependent linear transformation. If you then define a transformed velocity field in a natural way and define transformed stress tensor using a little bit of differential geometry, and you use the physical evolution equations, you can define transformed evolution equations for the transformed quantities that are entirely valid in the transformed frame and only depend on the transformation. So then if you impose shear through the transformation and make the system periodic in every direction, you now have Lees-Edwards boundary conditions. And then you can perform this matching between MD and continuum. OK, so with all that, I'm going to show you some nice movies of shear banding in metallic glasses. So all these results will be on a 512, 512, 256 cell grid. This gives us 67 million grid points in the bulk. And then that linear system has 67 million squared points in it. Of course, we actually don't store this matrix. It's very sparse, so we do something more clever, but it's a very large linear system. And we'll look at initial conditions in the chi field, which sort of sets the dynamics that are normally distributed with a mean mu and effective standard deviation sigma. OK, so the basic projection uses these parallel plate boundary conditions I showed in the previous slide, while the transformation method will look at simple shear and pure shear, which can be specified here. And for simple shear, we'll do Lees-Edwards boundary conditions, so it will be periodic in the z direction as well. And every one of these simulations takes about 4 days on 32 threads on one of our local desktops. OK, so we'll start with the basic simple shear projection, no transformation here. This is the effective temperature field that we're visualizing. So you can see shear bands form in the effective temperature field. It's sort of a proxy for the amount of plastic deformation occurring in a given location. This is the Lees-Edwards simulation. There's sort of a preference for vertical shear bands, vertical connecting shear bands to form in Lees-Edwards versus basic simple shear. And then this is pure shear, where you can see all these nice diagonal shear bands forming, propagating across the material. So I'm just going to leave these running in the background. As a conclusion, metallic glasses are a very promising new class of materials, but they're difficult to simulate using traditional methods. So we devised a new algorithm based on an analogy to the Navier-Stokes equations, which lets us simulate large system sizes and long times. And the transformation methodology enables us to connect MD simulations to continuum scale simulations. Future directions are actually performing this statistical matching procedure so we can compute the effective temperature from a given MD configuration, as well as extending the transformation methodology to the case where T depends on the local position. And in particular, we want to use this to study a necking instability in a stretch bar. And I'd like to thank my advisor, Chris Rycroft, our collaborators, Iran Bookbinder, Michael Falk, and Michael Shields, and then, of course, CSGF for supplying the funding needed to do this research.